Welcome to this second session in the series GeoBIM and Digital Twins in Practice Success Stories. My name is Magnus Ramon, and I'm the chair of TC 222. So first, just a few words as introduction. So shortly about the TC. We are a committee under the ISSMG, which is the International Society for Soil Mechanics and Geotechnical Engineering. And I'm leading the TC together with Michael, Mats, Jelena, and Raymond. We were initialized back in December 2020 and accepted by the ISSMG board in the spring 2021. And the main purpose defined in our terms of reference is that we are going to provide a platform for sharing and exchanging knowledge on BIM and digital twins in geotechnical engineering. And that's much of the background for this series as well. But we want to share the success stories that we have within the Geo Society when it comes to BIM and digital twins. For those of you who are not members, you can become members through the ISSMG webpage, which is this first QR code here. This has to be done through the member society from your nation, but this is the way to become a member of the TC. All our previous workshops and sessions are published on our YouTube channel. And then LinkedIn is the #1 communication platform that we use for reaching both members and even more non-members. And then we also normally present the PDFs of the presentations on our GitHub. This is not fully updated, but at least you can find some of them there. So today's session is going to be 2 presentations when it comes to GeoBIM and digital twins in practice. And the first one is Charles and Taurus, which comes from Geo in Hong Kong, also Civil Engineering and the Development Department of the Hong Kong SAR government, and which is Charles, and Taurus is from Arup in Hong Kong. And the title of their presentation is Development of a Regional Scale 3D Geotechnical Model in Hong Kong. So please, President Charles.
You're muted, Charles.
Hello, you hear me?
Yes, we do.
Yeah,
Perfect.
Thank you, Magnus, and hello everyone. My name is Charles Chen, and I'm working in the Geotechnical Engineering Office of the Hong Kong government. So today I'm going to present the development of regional scale 3D geotechnical model in Hong Kong, and I'm also presenting with Taurus from Arup, Hong Kong. Basically, Arup is one of the consultants that we commissioned to develop the methodology and also the model. Taurus, please. So what we're going to do today is mainly divided into 5 parts. First, I will talk about what it is, what the 3D geotechnical model, we call it 3D GM, is, and then I will talk about how to use the 3D GM. Basically, we develop some geoprocessing tool in our GIS platform that's called the 3D G-Info. And then Taurus will step in, and then we'll talk about overall workflow and then also modeling methodology. And then I will come back and then conclude the presentation by adding a few more remarks on how to interpret these 3D geotechnical models. Taurus, please. Thank you. So in Geo, we as a government office department, we have a role of providing a lot of geotechnical services to the industry. And one of the services that we provide is the setup of a geotechnical information unit. Basically, it is a library of GI records. Currently, we have more than 100,000 GI stations across Hong Kong. These records are stored in the so-called GIU, Geotechnical Information Unit. And then apart from that library side, we have developed the web-based GIS platform called the Geotechnical Information Infrastructure. We call it G-Info, or nowadays we call it 3D G-Info. So basically, the practitioners in the industry of Hong Kong, they can gain access to this website or the platform to download the GI report, PDF or AGS file. And this data is so valuable that they use it really daily. And then they will download it for their site investigation or their geotechnical assessment or their cost estimation of their works. And it's all effective, but for the ground condition to be fully understood, people has to spend time to process the data to build a model, to build a ground model, such that they can obtain useful information about the ground. So it's kind of time consuming. Taurus, please. So what we are doing is to accelerate this process, as you can see in the traditional procedure in this figure. We want to accelerate this process and improve the productivity of the industry practitioners. What we're going to do is to visualize this hidden information about the ground from these isolated GI records through the development of the 3D GM, and then display it in our 3D G-Info system. Taurus, please. So last year, we have completed the 3D GM in one of our major development area. We call it the Northern Metropolis, which is a very big, promising development area in Hong Kong. And we put these models into our 3D G-Info platform to let the practitioner to read it. And we think the 3D GM can accelerate preliminary geotechnical assessment and then optimize GI planning. Also, it facilitates site characterization by interact with different spatial data available in the G-Info, because in our GIS system, we have a lot more spatial data that the user can kind of show it concurrently. And then we also promote the informed decision-making process of our practitioner, and then enhance the cost estimate of our geotechnical works at early project stage. And also these 3D GM can form part of the digital twin model to support the new town development. Taurus, please. And to help the user to obtain useful information from this model, we have developed some geoprocessing tool in the 3D G-Info platform that include the things that you see in this video, the slides tool, and then also we have a tool that show the distribution of geotechnical units at defined vertical datum. And here are some more technical detail about the 3D GM. 3D GM is actually a preliminary geotechnical design ground model that is comprised of a maximum of 10 defined geotechnical units, which Taurus will explain it more in detail. And these geotechnical units are relevant to the Hong Kong foundation design. Also, we are adopting a modular approach to build this model. We are not building one for the whole Hong Kong. We are building in a map sheet, map grid base. where each model is about 750 meter times 600 meter size on plan. And also these geotechnical units, they are visualized by a basic element called voxel. If you look closely at the geotechnical unit, the different colors, they are actually made of smaller element, which with a resolution of 1+1+1 meter. And this voxel contains a value. We call it voxel value. And then basically we assign some value that corresponds to some geotechnical unit, and we can put it in the GIS platform, and then we show it in this way. Taurus, please. Also, we have pile feasibility check that is one of the geoprocessing tools that we develop as well. And then we have some input and that the users can put in. For example, they can put in the building boundary, loading parameters, foundation type, and the capacity and diameter. And then the tool in the platform can actually output the minimum number of piles required and the reference piling layout. And then this layout can be visualized in the 3D GeoInfo with the 3D GM. And then the system is actually flexible. You can actually add or remove these piles, and then we calculate again. And of course, the result can be downloaded in an Excel file. So it's very convenient for all the practitioners in the planning stage to estimate the quantity and the cost of the foundations. And then so this is the first part, and I will hand over to Taurus to talk about more.
Thank you, Charles. Hello, everyone. I'm Taurus. I'm an engineering geologist working in Arup, based in Hong Kong. So next, I'll move on to the methodology and explain a little bit more detail on how we develop the 3D GM. So what you are seeing here is the overall workflow of 3D GM. First, we identify the geotechnical unit in the ground investigation stations, such as boreholes and also trial pits. And then we extract the elevations of these units and then generate the continuous strata, as you can see here. And then additionally, we model the ground discontinuities, including the geological boundaries and also fault structures, so that we can better represent the in situ ground conditions. So based on the continuous strata and also the vertical boundaries, we can then generate the voxel-based model representing our 3D GM. So we then can proceed to the visualization and also quality checking to ensure the reliability and also the consistency of the model. It is also worth mentioning that the workflow above are semi-automated by Python and also the S3 Address Pro environment, which can help to improve the efficiency and also the reproducibility of our workflow. So the regional geological setting of Hong Kong is rather complex. We have intrusive igneous rock, we have volcanic rocks, we have sedimentary formations. Because of this diversity, it is essential that our model includes different kinds of geological units that are sufficiently representing their distinct geotechnical parameters. So you are looking at the geotechnical unit framework adopted in our model. So these units are considered the most relevant to our engineering design and practice in Hong Kong. So at the surface, we have artificial fields and also superficial deposits such as colluvium, alluvium, and marine deposits. And below them are the weather materials derived from the underlying bedrock. So we further classify these materials according to their soil stiffness using the standard penetration test and values, which is a very typical parameter to represent the soil stiffness in situ. And the bottom layers are the bedrocks, which we divided into three major rock types. These rock types exhibit different geomechanical properties. So some of them are further subdivided into different categories to reflect the variations in presumed bearing capacity for foundation. So we adopted this division method based on the foundation design guideline published by the building departments in Hong Kong. So there are total 7 continuous surfaces that we model, including the ground surface and also 7 types of geotechnical strata. So each of these strata represents the top boundary of a specific geotechnical unit. Using the ground investigation data, we extract the elevation points of these boundaries, and then we interpolate between them using the TIN method with linear interpolation. This will allow us to generate the continuous 3D surfaces from discrete GI data. We also have a supplementary step to further adjust the surfaces after we generate the surface for the first time. So for those deeper boreholes that do not encounter all geotechnical units, we found it essential to adjust the strata to make sure that these surfaces reflect the actual ground conditions more accurately. So in addition to modeling the continuous surfaces, we also incorporate the geological boundaries into the model. So how we define the rock types is that we have certain points of ground investigation points, and then we use the Thiessen polygon method. It works in a similar way to TIN by dividing the area based on the GI approximation. Once we have the distribution, we can then sort of chop the bedrock units into chunks, giving us the vertical boundaries between different rock types. So we also allow the boundaries to be inclined. If there is strong evidence occur from the geological map or the GI factual data, so we can further improve the accuracy of the models, especially for those areas where the GI density is very sparse. So what you are seeing here are the 2 examples of the inclined geological boundaries integrated into the 3D model. So you can see the relationship between the inclined boundaries shown in pink color here and also the bedrock model. While the other example has a rather complex cross relationship between 2 faults. So by specifying the dip direction and dip angle of the boundaries, we can actually project the 2D geological map into a 3D visualization into a 3D GM. So this will allow us to capture the structural features more realistically. So here's showing you a bigger extent of the model located in the northwest New Territories of Hong Kong. So within this 2 kilometer wide area, there are 3 types of bedrock identified. So to define the rock type distribution, we integrate 2 sources of information. One is the data-driven distribution, directly derived from the factual ground investigation data, and the published geological knowledge, including the map geological boundaries as well. So by combining these 2 sources, we transform the raw factual data and also interpret geological information into a more analytical and consistent geotechnical model, as shown here. So this is one of the models located in the Sun Tin area. The bedrock layer replicates the rock type distribution over here. So this model provides a simplified representation that highlights the changes in rock type in this area, which can sort of support the geotechnical engineer for further investigations. So moving on to the last technical step. Just a quick introduction. A voxel is a volumetric element. So it is a 3D pixel. This type of representation is particularly suitable for irregular and also fragmented structures, such as terrain and also geological formations. So it is well suited for our 3D GM use. And the model is stored in NetCDF format. As Charles mentioned earlier, the 3D GM has the resolution of 1 meter in all 3 dimensions. So each voxel cell is assigned a geotechnical unit based on the strata surface and also the geological boundaries we defined earlier. So by stacking and assigning those voxel cells layer by layer, we can then generate the full 3D GM using our in-house Python script. So to wrap up my session, here shows a short video slicing through one of the models. So this is very useful to visualize the internal structure of the model. We can also display the 3D borehole sticks in the same environment. So it will allow us to do quality checks and also compare the model directly with the factual data in detail. So next, I will hand it over to Charles for the last bit of our sharing.
Thank you. And actually, while making these models, we hope every model is accurate, but in reality, it's no model is accurate, actually. Accuracy issue is unavoidable, and then it's important to let our users of the 3D GM know the sources of inaccuracy before they use it. For example, there are 4 types of common sources. They are the natural variability, the GI data, availability, quality, the relevance of the interpolation method to the actual ground condition, as well as the level of professional geological input. These all form the accuracy or contribute to the accuracy of this kind of design ground model, just like 3D GM. Pause, please. So we try to ensure a proper interpretation of this model from the user by implementing several measures. First, we see on our top left is the 3D borehole stakes, which is a complementary data set with the 3D GM. So while the user read the 3D GM, they also know where the borehole is. And also on the bottom right is a distance to nearest borehole contour, or you can call it a borehole proximity plot. It tells how far the generated ground condition is to the known data points. And of course, the GI list can be downloaded. And also, while making these models, we have documented our methodology into a very nice documentation, as well as the data set details. These kind of documents that can be they can be downloaded from the 3D G-info. And also, we put up caveat on all the 3D GM, and we hope to remind all the users about all the assumption mix and then all the critical aspects that they should be aware of, and the aspect they have to verify independently. Basically, the users has to be reminded that this model 3D GM is a preliminary reference model. They are not a substitute of a thorough density and site-specific GI. And to use it responsibly, they should read it, and then they plan their GI and then exercise their professional judgment and then mitigate the risks accordingly. So that's it. Thank you. And I hope you now understand more the Geo's work in turning data into insights and then drive decision making using digital tools. Thank you.
Thank you very much, Charles and Taurus. Highly comprehensive presentation, and I think we have received a few questions. I can walk through them, starting from the top. So, what soil parameters are included in the database?
We that it touches on the topic of the geotechnical unit that we use. In our geotechnical units, we actually define it before we model, and we use it. We use 10 geotechnical units like this, and then for the soil parameter side, it's not that really much, because this kind of geotechnical unit basically is more about the rock type or soil type. And I can elaborate a little bit more about the CAT 1D or 2 things, because it's very specific to Hong Kong practice. So CAT 1D, 1C correspond to igneous or volcanic rocks, and then they are determined based on the strength of rocks, the grade of the rock, and also the TCR, these sort of things. So basically, they are rock properties. Okay, CAT 2 is similar, but on meta-sedimentary rock. So for rock is something like this, but for soil, the only thing that is relevant to soil property, I think, is the SPDN value. So we divide it into 3 parts. Why we're doing 100 and 200? Because the foundation practice in Hong Kong use these services to define the bottom level of our piles. So that's why. So we are very practitioner oriented in thinking about what geotechnical units we adopt.
Thank you. All right. The next question is, you touched a little bit into this, but maybe we can repeat. How is uncertainty handled, illustrated, and communicated in the model?
Yeah, that is very important, right? I think everyone agreed that uncertainty is very important. And then right now, these models, we are not doing some explicit uncertainty quantification. What we're going to do is just to point out the sources of these uncertainties. And then we will let the users to use their professional judgment to see this model in this particular area, which source is more significant, and then they should be more aware. For example, for the GI data variability, that figure, the red dots there are the GI points, the GI station, but you can see on the left there are no GI points. So when you interpret the model in those areas, you have to be extra careful, and then you have to understand the model, the ground condition shown there is a result of the interpolation method. So in this way, we try to alert our approach is to try to alert the user more, and then let them use their judgment to understand, okay, the degree of the uncertainty embedded in the model. Our approach is this kind. Of course, there are a lot more method to quantify uncertainty of ground model explicitly, and there are lots of academic research on this. Yeah. but our approach is more about the qualitative side.
Yeah, nice. Did you want to add something, Taurus?
Yes, just to supplement a little bit more, is that yeah, there are a lot of quantitative method to sort of quantify the uncertainties in ground model, but Geo is very helpful on sort of let the user be aware of what actually we need to be cautioned when using this preliminary model in the early stage of a project. Is that they also establish this the distance to nearest borehole contour, so it can basically tell you, give you an instinct that where the boreholes are located, how sparse or how dense are the boreholes in the particular interest area. So I think we need to sort of pair the model together with this map together, so that the users can have a more comprehensive understanding on the ground conditions. Yep.
Thank you. Okay, we have a few more questions. What is the benefit of voxel ground models over boundary surfaces such as meshes, NURBS, etc.? Using voxels in simple ground models like here is not memory efficient.
Taurus, you have any view?
In this stage, the 3D voxel model is the purpose of this is to let the practitioner or even designer to have a quick preview on how the ground conditions look like when they first receive their project details. So it is for the geotechnical engineers to sort of understand the ground condition very quickly in the preliminary design stage of the model. It could not sort of replace the site-specific detail even in the design construction stage. So if for the detail stage, we will need to be more aware of using this kind of model. Maybe you need to build a very high resolution with project specific borehole data to build your own model. But so the purpose of this 3D GM is more like help you to understand quickly in the regional scale level how the ground condition look like.
Yeah, and I have a point to make. In fact, in our platform, the user can download the original services that is used to create this voxel-based 3D GM. So these services are we can be team services. I don't remember correctly, but those boundary services can be downloaded, and then they can download it and then use it in their desktop software. And why we are picking the voxel, because we see a little bit of value in the use of voxel value. A voxel value is like a digital data that is stored inside a cubic meter volume, and that it has a potential of containing even more data than the geotechnical unit. For example, we can put engineering properties into this voxel in the form of voxel value, so that that is why we picked voxel in the very beginning. But of course, if you are asking for boundary services, yes, we have. We are making it available for download on the 3D Geinfo platform. So, yeah.
Okay, thank you. All right, I think we need to shortly wrap up the Q&A, but we have 2 more questions. So maybe some fast answers on the last 2 questions. Let's see here. What GIS tools algorithms have been used in the GM generation?
Taurus.
Yep. So for surface modeling, in this slide here, so the continuous surface strata were modeled using the triangulated irregular network with linear interpolation. So we call it TIN. So you can see just drawing the straight line over. And then once we have this continuous surface, and then we will go into the modeling method. So first of all, we'll use, of course, Python script to sort of assign the geotechnical unit one by one here. So it is sort of a parallel assignment of voxel unit into the voxel cells. So it is not, there's no any fancy method. It's just Python array, something like that, that we can quickly model and assign a geotechnical unit into this cube. Yeah, I hope it answered your question.
Yes, perfect. Thank you. And then the final question. So what is the smallest amount of data needed to create such a 3D model?
It should be 3 boreholes, I think, because we're using triangulation, and then to make a triangle, we need 3 points, and then if it connect together, and then it will form the model, but it will be very flat surfaces, and then it will be a very simple model.
All right. Thank you. Okay, I think that concludes the Q&A for this session. Thank you everyone for posting questions. And thank you, Charles and Taurus.
Thank you.
Thank you.
Yes, again, thank you for a very nice presentation. That was very interesting and impressive to see the work you've done in Hong Kong on these models. Yes, now over to the second presentation, which is going to be held by Eleni from Deltares in the Netherlands. And the presentation has the title, Digital Twins for Water Safety, a case study of the Amsterdam-Rijn Canal. And again, also here you can ask post questions on the Slido, either through the chat where it's a link, or you can use the QR code which you see here. Please, Eleni.
Yeah. Can you hear me first, or?
Yes, we can.
Okay, that's great. And then I will share my screen. Hopefully you can see that as well.
Yeah, now we can see that screen. Perfect.
Okay, so thanks, Magnus. Like Magnus said, my name is Eleni Smyrniou, and I work for Deltares, which is an institute of groundwater and soil in the Netherlands. Today I will present something on the digital twins for water safety, specifically a case study we did for Amsterdam-Rijn Canal. And then I would like to start by saying that I work for the Department of Safe and Resilient Infrastructure, where we do a lot of things, but basically we focus on all aspects of infrastructure. So here you see we start with subsurface. We do a lot of data-driven and AI methods and research to do subsurface mapping. Then in asset performance, a lot of reliability, risk assessment, and monitoring performance data. And finally, we zoom out and we look at the network resilience, how certain hazards impact areas, and how to make decisions in certain situations. Like I said, the institute is based in the Netherlands, so this kind of informs the whole presentation. And actually, what is very important to understand, I think, is that in the Netherlands there have been various big flood events, which lead to policy and research. And you can see here a list of all the the stuff that happens in every flooding event, with the last two being the research institute being opened in 2008, and also risk assessment standards for the whole flood defenses. So what does that mean? That means that if you are a Dutch asset manager, you have a lot of responsibilities, from daily management, where you have to inspect your flood defenses, and you have to make sure that your flood defenses will be operational in high water situations. Every 12 years, you have to do a safety assessment of the whole levee that you own or some other asset. And this means that that you have to continuously acquire data, and you have to update your models using the national assessment tools, and you have to report back to the ministry. Apart from that, if of course you see something that is not up to standards, you need to reinforce this flood defense. And this circle happens continuously every day. And this is what the digital twin is about, and this presentation is about. So I will jump into our specific case study for the Amsterdam-Rijn Canal, which is a fairly long canal in the Netherlands, connecting Amsterdam Harbor with eventually Germany. It's very busy, 100,000 ships pass per year, and there is a lot of infrastructure also on this canal, with very big sluices and 37 bridges and some tunnels as well. So the question we got from the Ministry of Infrastructures in the Netherlands, which is the asset manager of Amsterdam-Rijn Canal, is that if we can help them envision a digital system that helps them do asset management in the Amsterdam-Rijn Canal. And it should be transparent, and it should make predictions, and also explore the real-time capabilities of such a system. And this we did as Deltares, as the geotechnical expert, together with Soldering, that they were responsible for the visualization and the APIs. I will explain more about this in a minute. But basically, then the goal becomes to build a digital twin, which is a proof of concept for specific locations, so that the ministry then can kind of deploy it for various locations and to help more colleagues than now. The two locations are the Betuwe Pond, which only consists of levees, and here we test on macro stability, and the North Pond, which includes seed pile walls, and here we look into the degradation of the seed pile due to corrosion. We use geotechnical parameters, structural parameters, geometry, subsurface, and geohydrology to assess these assets. And at the end, you end up with a factor of safety throughout time in specific conditions. So what is a digital twin? Maybe a lot of you know already, but it's basically a copy of a virtual model. In this case, we want to be able to integrate and visualize all the data that we have, show certain behavior under certain conditions, support the monitoring that they do, and also provide some kind of visual tool to also see how the advanced methods we create as researchers, how they can be plugged into such systems. So I'll start with the first part, which is the flood defenses. You see here quite a sunny day in the Netherlands. And basically, this part connects the Waal with the Lek rivers. And here I go back into the responsibilities of the asset manager, where we try to make certain functionalities which will help the asset manager do their work. So for the daily management, we focus on near real-time stability assessment, and we try to see what would happen if there was a high water event. For the safety assessment, we keep all of the geometry data and subsurface data up to date. And for the reinforcement, we allow the user to do scenario testing with mitigation measures. A bit on the geotechnical ingredients and assumptions. Here you see that we actually do macro stability assessment using Uplift Fun, using the distability software, which we also develop, which is an open source software, so you feel free to download and play around with it. Apart from that, the geometric and external factors, this we take from the national LiDAR collection, which is the NHN. And this is open source data that we can just retrieve through APIs. The geotechnical parameters stay the same as the asset manager has defined them, and we will not change them in the digital twin. But what is dynamic are the hydraulic characteristics. So basically the water table position and the pore water pressure, which is changed through rainfall, evaporation, river data, and sluice discharge through a machine learning model. Basically, creating this model, we can make predictions on the phreatic line for every cross-section. So I will dive now into the digital twin architecture, where we will build together the digital twin. Otherwise, it's too much information at once. You see here on the right top side, we keep in our minds always this loop of the asset manager. And on the left side, you see the four main components, which are the external APIs. So as we do dynamic analysis of the system, we need to continuously integrate data from open source locations like the weather forecasts and the water level forecasts for this river. Apart from that, we have a storage bucket where we just store every calculation that we ever made. We store the cross sections and the hydraulic models. We also have the viewer. The viewer is just there to visualize the data. It does not do any calculations. All the calculations happen in the RC backend, which we will fill in now. The first thing we need is the hydrological models, which get updated once per day automatically. And these are stored in the bucket. Then we move up to the daily management. What we do in this case is once per hour, we run a near real-time stability assessment for every cross-section of the levee. And then we add you can see on the right side, the viewer communicates with an endpoint on the back end through this command, as you see here. So for every step I will explain now, we will add another command at the endpoint. You see here, every 4 hours, we also check that the water level in the canal is not exceeded. If it is exceeded, we trigger a prediction of the phreatic surface for the next 24 hours, and then we run a stability calculation for every cross-section. Apart from that, the user can also trigger scenarios for specific hydraulic characteristics, for specific cross-sections, but also using a selection of mitigation measures. And finally, we also have the safety assessment, which is just historical data that can be added also, it can be also connected to the viewer. And then now I will show you the digital twin. You see here an overall view with a subsurface model that we use a geotop. And you see here quite the Dutch situation with a lot of clay and a lot of peat in this area. So you can also visualize this. It helps the asset owners visualize how the underground looks in this area. But more to the safety assessment. You see here the bird's eye view of the whole levee with the safety factors on the west and the east side, and how they change in terms of kilometers. This is calculated on a specific time step. This was Friday, but this is still running. If I click on a certain location, you see a dashboard opens with a certain safety factor. And also we have connection to various sensors that show the water levels, but also the precipitation. And this is connected with this API that and this backend I explained before. So you see here there is also a sleep circle of the last calculated stability assessment, which is also dynamically taken from the viewer and visualized. Apart from that, I move on to the safety assessment. So we were now in the real-time calculation. I will go into the prediction tab, where you see there is no prediction being made because the water level has not exceeded a certain threshold. After that, we have the historical calculation, which is a high water scenario we have previously calculated. And you see how the bird's eye view again of the whole area, and also how the safety factor changes throughout the timeline of this event, with areas becoming yellow or red. This is again calculated for the whole area, and you can scroll back and forth like I'm doing here for certain locations. What you can also do is actually click on a certain location and see how the factor of safety develops through time, also how the water levels develop through time, and also how the sleep circle, I will do it in a minute, develops through time. Now I'm clicking through different cross sections to kind of visualize that everything is dynamically accessed. And also you see here that the sleep circle is changing throughout this high water event. The last function, like we said, is the mitigation measures. Here, actually, the user can run a simulation, so the user triggers the simulation that will be calculated in the backend. Here you see you have to select a name for your simulation. And after that, we will select certain measures that an asset manager can take during a high water situation. What we have for now are big bugs that you can place for stability on the passive side of the sleep circle. A berm that also supports during stability, or in this case, you can also close. We have cases where we close the ditch in order to prevent also diminishing of stability. You see me here selecting certain measures on certain locations. And certain measures cannot be placed on top of each other. So you see here this is the berm cannot be placed together with the big bugs, but you can add you can close the ditch on several. You can close the ditch and place big bugs on location. Apart from that, you need to specify the water level, which you do on a specific date. Or you can choose the historic scenario we calculated before. And then you can also choose which time step you use in this case. And after you save this simulation, you can actually start it. In this case, it will take 15 minutes to run, and this will start calculating on the background. And then here you can see that another one I did before. It is saved, and I can always come back to it if needs be. And basically, the results are visualized in the same way as the previous tabs. And seeing the time, I will skip this part. To also show you a small teaser about the north pond, which is the part of the canal with the seed pile walls. And then basically what we do here is that we have the seed pile walls that were installed 50 years ago. And the question here is, based on the observations that we have made, how much lifetime is left before we need to remove this seed pile and replace it. Again, we have a similar view with along along the canal, how much lifetime is left for the seed piles. And then you see here, if we, for each time step, how the safety factor changes. All of this is calculated on the background, and then you can click on a certain location to actually visualize how the seed pile is deformed. In this case, we visualize it with a column, but we can also think about maybe doing it with a whole seed pile. Yeah, and apart from that, you see here that there is a corrosion model behind all of this calculation, which can get updated with values from inspectors. And this is actually how far we have gotten with this case. So I would like to give you some conclusions and next steps. This project that we did, what you see actually on the screen today, was made by having a lot of workshops with the asset management managers. And yeah, it's a convergence of all of these talks with them. So keeping in mind what they really want was also a very important part of the project. And some things that we are going to look in the future is also having the ability to change the ground condition. We make, like I said, we make a lot of AI subsurface models, so we would like to plug them in here. And also for the Betuwe pond, expanding with different failure modes, and for the North pond, also incorporating our research into the tool. And I would like to thank you for your attention.
Thank you, Eleni. That was very impressive. Is this in production currently?
Yes, this is running. Do you want to see it? This is currently still running, and we have it in production. And now what we want to do is actually figure out how we can kind of distribute it among the ministry so that it is used by everybody there. But this is more something that we as a research institute cannot do. The asset manager has to kind of incorporate it. Yeah.
We have received one question. It's about uncertainty. What is the uncertainty in the calculated safety factor, especially when it comes to uncertainties in the site conditions?
Yeah, so actually, that's a very good question because like I said, we have a hydraulic model that runs behind this fancy digital twin, and there is uncertainty in the things that we predict. So it would be much better if we didn't display a safety factor, but the reliability of every cross section. And this is one of the next steps that we should do. Yeah. And then inherently you have the uncertainty in that value if you switch from safety factor to a reliability index.
All right, we have another question coming now. So could you explain a bit what has been the main challenges to actually come this far as you have done now?
So there are several challenges. Some of them are technical. So actually having all of these tools that are never being merged together to actually create that workflow, that was quite challenging. But also kind of proving to the asset manager that they can use it, and what is the question behind their daily operations. This is the most challenging thing, actually getting to the user and seeing what they really, really want instead of what is a nice technology push for us to do. Very important.
Okay, more questions coming in. How large is the team behind this, and what are the development and ongoing maintenance costs associated with your digital twin framework?
Yeah. Okay, so the development team is quite large. As you can imagine, it's not just me. From the scheduling side, there are 3 people that work on this. From our side, actually, our whole department is involved in this in one way or the other. Like I said, we use a software that has been developed here in-house. These are also indirectly part of the team. The seed pile models that we develop are also like 5 people that are working on this. So the whole department is kind of involved in this, indirectly or directly. And about the costs, until now, we haven't kind of reached very high costs. The minimum platform that we use is something that we have in-house in Deltares. And if it doesn't exceed 1 terabyte, which it will not exceed 1 terabyte, we have no cost associated to storage. And the computing platform is something that they have in scheduling, and it's also quite cheap, to be honest.
Well, it's thank you for your answer.
Yeah.
And it's a very impressive platform. I think that concluded the question session. Thank you everyone for posting questions.
Yes, I think that was all the questions. So, and thank you, Eleni, for a very interesting and impressive presentation. That was really nice to see what you've done on this digital twin. I think that wraps up our session today. Again, a big thank you to Taurus, Charles, and Eleni for presenting their work. It's been very interesting to see. We will hopefully have our next session in this series in end of April. We're planning for that, finding two new presenters for that session. And other than that, we will also have a member meeting during the international conference, which is coming up in June in Vienna, where there will also be some presentations related to the topic of BIM and digital twins. Yes. Again, thank you to the presenters, and thank you for the listeners as well that you joined our meeting today. And I hope to see you all back in April. Thank you and goodbye.
Thank you. Bye-bye.
Bye.